As technology has developed over the past decade, methods to create, design, and test engineering design models have improved and have gotten better and easier. Better to the point that most mathematical formulas used in engineering no longer need to be calculated by hand, but rather we use digital softwares to calculate them. And in this video, I'm going to give you a basic understanding of what FEM is, why it's important, and why it's used in engineering design. To find out more, stick around. Hey everyone, I'm MJ Sanga, your average engineer. To get to the topic of this video, when it comes to engineering, design engineers have to go through a whole range of steps in order to design the product. One of these steps is performing simulation. Designing a part is one thing, but we need to know how it performs under various conditions. Let's say we have a product that we want to design. We've created a 3D model of it, which is alright, but we're not sure if it will hold up under operation. And to make things worse, we do not have a physical prototype, only a 3D prototype and 2D sketches. So then how do we solve it? We can use what is known as FEM, or finite element method. The finite element method is a popular method for numerically solving differential equations arising in engineering and mathematical modeling. Typical problems of interest include traditional fields in structural analysis, fluid flow, heat transfer, and transport movement, and so on. In layman terms, it's the use of mathematical formulas to analyze a part. This can help us identify how heat is transferred through the part and how much pressure or force the part can take during operation. This is done by subdividing a part into equal areas or domains known as finite elements. We can then apply partial differential equations on each domain to see how each area performs. And this entire process is called finite element analysis. During this process, we can combine all sets of element equations into a global system equation to find the final result of the entire part. This method allows us to identify which areas have weak points, because not all values are the same. Some areas are flat, some areas are curved, and some are a bit of both. However, most of the parts these days are a bit complex, and it could take a lot of time to accurately find an FEM result. This is mostly because of human error. To improve accuracy in an experiment, engineers have to perform it more than once. And to make it even more accurate, more than one engineer has to do the test. Now, this can take a lot of time, and with deadlines approaching, it doesn't look very efficient. To solve this entire problem, there are many softwares that engineers use to help with finite element analysis. Now, in order to incorporate finite element analysis into your design, you need to have a few things in mind before you do the analysis. Firstly, what is your goal? What are you trying to achieve during this analysis? Are you trying to find the stress? Are you trying to find the deformation? Are you trying to find the temperature? If you do not have a goal, then the entire analysis is kind of pointless. Next, we need to consider the geometry of the part. We need to consider the dimensions of our design and the material properties as appropriate. Next, we need to have constraints. We need to have an understanding of how the system works with its surroundings. Is it bolted? Is it welded? Weight is sliding? Is there contact with other parts? Those things need to be considered. Next, we need to have loads. These are the magnitudes, and we need to know how much should be applied on each part. Next, we need to have a risk assessment. What are the risks associated with this product, and how important is it to get the design done right? And lastly, we need to have an analyst. We need to have someone who's experienced with putting loads and constraints. These are the people who are more likely to give you better results of your design. Once you have a few of those things, then you are ready to incorporate FEA into your design. Now, to explain FEA further, we'll first need the software. I'm going to use Ansys Workbench to explain how to perform a finite element analysis. By the way, if you haven't subscribed yet, please subscribe. And if you enjoyed this video, please hit the like button below. Now, our goal of this design is to perform a finite element analysis on a shock absorber. We are to test out its deformation, its strain, its stress, and we are to find out how it operates under certain loads. So we begin by opening ANSYS Workbench and we select Static Structure. ANSYS has a lot of options that allow you to perform different tests such as CFD, model analysis, and so much more. In Static Structure, we're able to find the deformation, stress, strain, and any structural effects the shock absorber will get during operation. Now, under Static Structure, we have many tabs we have to fill in. In the first one, we have Engineering Data, which is automatically filled. This holds the type of material that can be used during the analysis method. By default, steel is selected, but you can change and customize the value of the material. Since it is filled, we'll go to the next tab, which is Geometry. In this tab, we import the assembly part we created. You can also use this to design the parts individually, but I use SolidWorks to design this. Please be noted that it's best to import the part as a step file, and after we're done importing the model, we can move on to the next tab. The next tab is Model. In Model, we have to include the mesh, which is the finite elements I was talking about at the beginning of this video. There are many options under the mesh that can help you refine the mesh. The more refined the mesh is, the more accurate the results are. For this part, I just selected sizing. Then we're going to add the needed variables such as fixed support and force. For fixed support, we're going to hold down the lower part of the shock absorber, meaning that during the simulation and analysis, it will not move. Then we're going to add a force which is at the top of the shock absorber. For the force, you can add different values over time to test out how the shock absorber performs. Then under Solutions, we add the results we want to find after the simulation is complete, such as deformation, strain, stress, and so on. Next, we click on Solve and then we get our results. Once the analysis is done, you can see how the shock absorber performs under different loads and how its deformation, stress, and strain is under those certain loads. We can change the parameters to see how the product operates and spot the weak points in the design. If we do find weak points, we can change the design by fixing the dimensions or adding a different material. There are many advantages of using finite element analysis. Designing parts are one thing, but in order for them to be accepted by the manufacturer, we still need to know how they operate under certain loads and constraints. And finite element analysis helps us analyze each part and product. One of the advantages of finite element analysis is that you can check if your design is on track during the design process. With finite element analysis, you can check the varying conditions of your design, such as buckling, heat, stress, strain, and so on. It's a powerful simulation tool used alongside CFD and motion analysis. And by including finite element analysis as part of your product design, you can simulate real-world effects before you create a physical prototype, which is an advantage. Another advantage is that you can also check calculations when hand calculations are a bit too difficult. The calculations used in finite element analysis are a little bit complex, and if engineers were to manually solve them, there would be human error. And in order for human error to be reduced as much as possible, engineers would have to solve it more than once, and more than one engineer would have to solve these equations. However, with software such as ANSYS, SolidWorks, and many others, you can easily reduce this time because most of the equations are automatically solved. Engineers can then check with the calculations from these softwares and compare them with the calculations they made manually. One other advantage is that you could design a product with accuracy. Finite element analysis enables an immediate increase in material analysis during designing. This is because we're able to see how all physical stresses affect the design. Because of this, the design is enhanced. Finite element analysis allows designers to better determine how stresses within one piece will affect the material in another separate but connected piece. So the more accurate you're able to get a product, the longer it will perform during operation. Another advantage is that you can also create time-dependent simulations. For example, car crash simulation, in which deformation in one area is affected by deformation in another area over time. This helps design engineers find ways to strengthen the material or the part that is being created. Designing a part takes time. We need to consider the safety of the people using it. And in this era where we're going green, we have to consider how the part affects the environment as well. And by using finite element analysis, we're able to speed up the design process as well as improve the design that is being created before we could even create a prototype. By the way, if you want to learn more about design engineering and the steps taken, you can watch my video on generative engineering right here. And if you enjoyed this video, please hit the like button and don't forget to subscribe. If you want to watch more of my upcoming content, please hit subscribe and the bell icon to be notified as soon as possible. Thank you for watching. Have a great day and God bless you.